Okay, so we left off with Hoffman elimination, and you guys remember Zaitsev and Hoffman, so we talked about those in detail. But just when we talked about Hoffman and Zaitsev elimination before, the leaving groups were either a halogen, so a halide, or like a tosylate, something along those lines. But now what we're going to see is, instead of taking an alcohol and then converting it into something like a tosylate and then doing an elimination, we can also do an elimination with an amine. Okay, so this is something new. And what we're going to see is that when we do the elimination, that we preferentially get the Hoffman product, which is the less substituted alkene. And there's a good reason why that happens. Okay, so you guys remember that whole thing of exhaustive alkylation? So I'll just write exhaustive so I don't get too tired. Anyhow, so the exhaustive alkylation. So what happens is if you take something like this, so this is just isopropylamine, and you treat it with a whole bunch of methyl iodide or iodomethane, it's going to keep alkylating and alkylating and alkylating until you get a quaternary ammonium salt like this. Well, it turns out that the portion that's highlighted in green is a good leaving group. Now, an amine is a terrible leaving group, but once you have this trimethylamine, it does make a good leaving group, okay? So you'd end up with this, so this would be called a trialkyl ammonium iodide salt, is what you would call this, okay? So after you do the exhaustive alkylation in the first step, then what you do in the second step is you use silver oxide. And if you're like, well, that silver doesn't come up a whole lot in this class. Well, there's a reason why we use silver oxide as a base instead of something like sodium hydroxide or potassium hydroxide. And I'll explain that to you in just a second. But the idea is this. After the first step in this reaction, what you would end up with would be this. So you'd end up with this quaternary ammonium salt, and then the silver oxide behaves as a base, and you pull off this proton, and you end up with the Hoffman product. So the reason why we do this, okay, is because, and I think I wrote it down here, so I don't have a ton of room here, but the idea is this, is that when you put in the silver oxide, after the first step, you're going to end up with your iodide ion, right? So you end up with the iodide like this. But then when you treat it with silver oxide, what it does is it swaps it out for, you end up with the hydroxide ion. So I'll write it in red here. So you end up with the hydroxide. And what happens to the silver is it precipitates as silver iodide. So that's a solid which precipitates out of the reaction mixture. And so now you have your hydroxide, which can abstract your proton and cause your loss of leaving group to occur, okay? Now, the book goes into a little bit of an explanation of this. I'm never going to ask you to write an essay about this or anything. Just remember that silver oxide is the base, but that's the rationale, is because silver iodide is a solid, okay? That's the whole rationale behind the whole thing. So once you treat it with silver oxide, you end up exchanging the iodide for the hydroxide. It does the E2, and you're done. And of course, you also end up with silver iodide, which is a solid from the reaction mixture. All right, so now it says here the Hoffman elimination, give the terminal alkene, or I'm going to highlight here Hoffman less substituted alkene. Now, why would that be? Because you guys know that there is also an alpha proton here, okay, or a beta proton here, rather. So why doesn't it abstract that beta proton? Well, it actually has something to do with the size of this leaving group. I mean, this leaving group is, I'll just put here, large leaving group, okay? It's very big, and there's a problem, not a problem, but there's a higher activation energy for abstracting the proton in blue. Let me show you what I mean. Okay, so let's say you were going to make the Zaitsev, okay, which is not the preferential product. If you draw the Newman projection, okay, between carbons 2 and 3 that are shown here, you see that when you draw the Newman projection, that, remember, the proton that's abstracted and the leaving group have to be antiperiplanar to each other. And when they're antiperiplanar to each other, you're always going to have a gauche interaction between the leaving group and the alkyl group, okay? So this is a gauche interaction right here. However, if you make the Hoffman product, then in that case, you see this proton right here. So if we look at the red proton in the leaving group, they're antiperiplanar to each other, but now there's no gauche interaction. So we'll say here, when you do the Hofmann, there's no gauche interaction. And so it has a lower activation energy. So I'll put here lower activation energy. Now this product is more stable. I agree with you on that. But since this one has a lower activation energy, that means you're going to form the Hofmann preferentially. Okay, so there we go. So it says draw the major product expected when each of the following compounds is treated with excess methyl iodide, followed by aqueous silver oxide and heat. So it says cyclohexylamine. So let's start out by drawing cyclohexylamine, okay, which is this compound here. So in the first step, you're going to treat it with excess methyl iodide. That's going to give you the quaternary ammonium salt, like this, okay, like that. Now I'm going to not put the iodide because I guess I could, but we're going to treat it with the silver oxide. So this is just going to be your intermediate. And then after treatment with silver oxide, and then we also put water and heat, what's going to happen is now you're going to have your hydroxide ion like this. And if this is your alpha carbon, these are your beta carbons. There's only one type of beta proton in this whole molecule, which is this one here. And so you're going to rip off this proton, form the double bond, lose your leaving group. So again, this is nothing more than an intermediate. And the product that you're going to form in this case is going to be cyclohexene, this compound here. Give me a thumbs up if you're with me on that. Does everybody follow my rationale here? And you don't have to draw in all these intermediates and everything. I'm just doing it for instructional purposes only, just to show you. And I know you know how to do all this. But anyhow, the next one, if we wanted to do R3-methyl-2-butanamine, so if we draw R3-methyl-2-butanamine, so I always draw it with a dash and then just check it. So 1, 2, 3. Yep, so that's the right compound. So here, let's just do it a little bit simpler this time. We'll write down step 1 is excess iodomethane. And if you're wondering, do we always use excess iodomethane? Yes, that's what we always use in step 1, okay? And then in step 2, we use silver oxide, water, and we heat that up. And you guys know how to draw a Hofmann product, okay? Let me just quiz you one more time, okay? If I wanted to make the Hofmann product, would I pull off this red proton or this blue proton? And there is no question designed to fool you in this class. Which one would come off to make the Hofmann product? Exactly. Thanks, Anastasia. Appreciate it. All right, so what we would end up with would be this. There you go. So not too bad, right? Not too bad. All right, we'll do the last one kind of quickly. So the last one, it says NN-dimethyl 1-phenylpropane 2-amine. So that would be, let's see here, if we have something that looks like this. So 1-phenyl, okay, and then we have 2 propane 2-amine, so NN-dimethyl. There we go. So we have this compound. Step 1, excess methyl iodide. Step 2, silver oxide, water. And we heat that up. Of course, you have to say it with an accent. And then you would end up with this compound. I'll just put pH for the aromatic ring. There you go. Another Hofmann product. So remember, this is the Hofmann elimination. So we always end up with the Hofmann product. And the reaction goes like this. Step 1 is excess methyl iodide. And step 2 is silver oxide, if you can read that, water, and heat. Those are the conditions for the Hofmann elimination. And again, why does it happen? Why do we get the Hofmann instead of the Zaitsev product? It's because the leaving group that you form is so big and bulky that if you form the Hofmann product, it avoids that, that gauche interaction, which causes a high activation energy. All right, there we go. So on to the next subject, which is talking about nitrous acid. And if you go back to General Chemistry 1, okay, you would have learned nomenclature of acids, sulfuric acid, hydrochloric acid, hydrobromic acid, et cetera, et cetera. But you would have learned something like nitric acid. Then if you remove an oxygen, it becomes nitrous acid. Let's say you had phosphoric acid, right? H3PO4. If it's H3PO3, it's phosphorus acid. If you have something like H2SO4, that's sulfuric acid. This is sulfurous acid, right? So you know where us acids come from. You take the ic acid and then you remove an oxygen. Well, it turns out the nitrous acid, HNO2, if you're wondering, why have I never seen a bottle of nitrous acid in a lab? Okay, there's a very good reason for that. It's because it's unstable, okay? Nitrous acid has to be made in a solution. So you don't just go pick up a bottle of nitrous acid at the store. What you actually do is you mix sodium nitrite. So you mix, let me write it down here, sodium nitrite and HCl together. And when you put those together, you can see this mechanism here. And I'm going to put here, will not ask this mechanism. What happens is after 2 proton transfers, you lose water from the oxonium ion and you end up forming this ion here, but you do have to know the structure of this guy. Okay, this is the nitrosonium ion, not to be confused with the nitronium ion. Okay, I had a student put up their hand one time and say, what, isn't that the nitronium ion? No, this one here that I'm drawing, this is for nitration. This is the nitronium ion. That was covered in chapter 18. That was for nitration. The nitrosonium ion is something different. Okay, you can see it's got 2 resonance forms here. And yeah, the one that would be, contribute more to the resonance hybrid would be this one, even though the positive charge is on the more electronegative element. In the one in the blue circle, both atoms have a complete octet, whereas the nitrogen doesn't have a complete octet in the first structure. All right, so that's how you form HNO2. All right, and it decomposes. Nitrous acid will be protonated by HCl to give you the nitrosonium ion. So if I didn't make that clear, what you do is you take sodium nitrate and HCl, it makes nitrous acid, but then the nitrous acid gets protonated, you lose water, and you form the nitrosonium ion. So that's what happens in your reaction flask. Now, again, the nitrosonium ion, just like the nitronium ion, is a very powerful electrophile. It's really unstable, and it will react with an amine as soon as it forms. So if it sees a primary or secondary amine, it is going to react. So it can react with a primary amine, and they can also react with a secondary amine. Okay, we don't look at tertiary amines. They don't react with tertiary amines. They're too sterically hindered. But with respect to primary and secondary amines, when we react a nitrosonium ion with a primary amine, there's a lot of useful chemistry that we can do with that. With a secondary amine, not so much, okay? And we actually start with secondary amines, and let me show you why they're not all that useful. So if we take a secondary amine and we treat it with sodium nitrite, so remember this is sodium nitrite, not nitrate. Nitrate is NO3 minus 1. Nitrite is NO2 minus 1. We end up forming this new functional group. This is called an N-nitrosamine, okay? And I will not ask you the mechanism on the bottom. I'll even write here, will not ask. But you see how the secondary, the secondary amine is a nucleophile. It attacks the nitrosonium ion. Then after a proton transfer, you end up with this N-nitrosamine. Now, if you're wondering, now why did you say this was not going to be super useful? Well, it's because nitrosamines are actually carcinogenic, okay? And maybe they do have a place somewhere in a medicine that I'm not aware of, but you find them in things like canned foods, like cold cuts, and you can see it found in beer, and what else? Fried bacon and tobacco smoke, all things that I enjoy. But anyhow, so there you go. So that's why we don't spend a lot of time talking about nitrosamines, is because they're carcinogenic, which means they cause cancer. Anyhow, so are you good with me on that? So this is what you can do. Secondary amine is you end up making a nitrosamine when you treat it with sodium nitrate and HCl. Okay, so a nitrosamine is, again, basically you're forming poison, okay, which is not super useful. Okay, so if you react a primary amine with sodium nitrate and HCl, of course, you form the nitrosonium ion, and then you can form what's called a diazonium salt. This process has a name. This is called diazotization. So you need to know that. Diazotization, or we can say we would diazotize this, group or something, this primary amine. This is a super important reaction because once you form a diazonium salt, okay, there's a lot of cool chemistry that you can do with these, all kinds of cool stuff. And we only kind of scratch the surface. Now, I'm not going to ask you this mechanism, will not ask. I'm not going to ask you the mechanism of diazotization, but it is here, okay? So with that in mind, let's take a look at alkyl diazonium salt. So if you have an alkyl diazonium salt like this, so if you have like an alkyl diazonium salt like this, right, because an isopropyl group is an alkyl, these are actually explosive. So explosive. And I don't know about you, but I generally frown on explosions in the lab. I don't like to do that, I don't want to blow myself up. So alkyl diazonium salt's not that useful for us. However, aryl diazoniums are super, it says here a bit more stable, but they're synthetically versatile. You can do all kinds of cool stuff with an aryl diazonium ion. So we'll put here, I'll highlight synthetically versatile. Now, why would this be more stable? It's because if you were to lose that as nitrogen, then you would end up with an aryl cation, which I've told you a million times is very, 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 very unstable. Okay, I should add another very in there. But so that's why aryl diazonium salts are okay. Now you notice that we're leaving out the counterion here, which is the chloride. Sometimes it's included, sometimes it's left out. But the bottom line is once you diazotize or form a aryl diazonium salt, it's very useful. You can put a whole bunch of different substituents in there. And that brings us to the next class of reactions, which are all named after one person. These are called the Sandmeyer reactions. And it's the reaction of an aryl diazonium ion. Again, the chloride is not shown here. Okay, you could put it in. It's just a counter ion. You don't have to put it in. So the aryl diazonium ion is reacted with a copper 1 salt. So you could pair a copper 1 salt, like copper 1 bromide, copper 1 chloride, copper 1 iodide, or copper 1 cyanide. And you can make bromobenzene, chlorobenzene, ionobenzene, and benzonitrile, all of these different compounds. And these, like I said, are called the Sandmeyer reactions. Okay, these are all named after the same person, Sandmeyer, who discovered these. Now, what can you do with these? Well, you could do Grignard chemistry with any of the aryl halides. And you guys know that we can take a nitrile and we can hydrolyze that with aqueous acid and heat, and that will give us benzoic acid. So now we have another way of making a benzoic acid derivative. So check this out right here. And this is kind of, just more discussion on what I just said. So if we take this compound, the compound on the far left, you could call this isopropyl benzene. The common name of this compound, I've told you a couple times, but this is called cumene. Okay, so cumene, first step is a nitration, then a reduction, a workup with base to make the amine. So after step 3, you would have this compound, the free amine, right? So you'd call that para-isopropyl aniline. Then in the next step, step 4, this is the diazotization. Okay. Now we have the diazonium salt. The next step, this is a Sandmeyer reaction. So Sandmeyer, that's going to give you the nitrile. And then in the last step, you hydrolyze the nitrile to the carboxylic acid. And so, like I said, now we have another way to make a benzoic acid derivative that we didn't have before. So that's kind of cool. Another reaction, so outside of the Sandmeyer, so we've covered the Sandmeyer reactions, which are these 4 reactions. There are other reactions that look similar to the Sandmeyer reactions in what they do, but they are not considered Sandmeyer reactions because Sandmeyer always involves copper X, right? So where X could be chlorine, bromine, iodine, or cyanide, okay? Another reaction is this one here, and you've probably never thought of this acid anytime recently, HBF4. This is called fluoroboric acid. I'll put in here fluoroboric acid. And there's no mechanism provided for this, but this is a way to install a fluorine on a ring. we haven't looked at any ways to install a fluorine on a ring so far. And this reaction actually has a name. It's not in my slides, but this is called the CHEM reaction. So the CHEM reaction. Okay, the CHEM reaction installs a fluorine. And the other one, the last one, is just treating the diazonium salt with water and cooking it up. That makes a phenol. And I always make a point of telling this to my students is that I just right here, not many ways to make a phenol. You know, what did we have? Like SNAR or something like that. So, you know, there's not a lot of ways that we have to make a phenol. So that's kind of cool. All right. And then there's one more reaction I want to show you. So we've got the Sandmeyer, we've got the Shemin, we've got the phenol synthesis, which is just taking the aryl diazonium and treating it with water and cooking it up. And the last one is treatment with this acid here. So this is hypophosphorus acid. So if you go from phosphoric acid to phosphorus acid to hypophosphorus acid, so this would be hypophosphorus acid. What that does is it converts the diazonium salt to just a proton. So it reduces it down to a hydrogen. And if you're thinking, what would be the synthetic utility of that? Well, let me show you. Remember this compound that we saw earlier on? We said this is a few minutes ago, maybe like half an hour ago or something. We said if you take aniline and you treat it with bromine, this is a strong activator. And so it just brominates the heck out of this thing. So you end up with this 2,4,6 tribromo aniline. Well, what happens is if you make the diazonium salt and you treat it with hypophosphorus acid, then you can convert this into the proton, and now you've got 1,3,5 tribromobenzene is what you would call this compound. And there's no other way that we know how to make this compound. Why? Because bromine is actually an ortho-para director, and they're all meta to each other. So you might think, well, it's kind of a weird compound, and it's kind of a one-off, Mr. Dion. Well, maybe so, but it is a useful compound, you know, depending on what you're looking for. And we have no way to make a compound like this except for using our diazotization and then replacing it with a hydrogen atom, the diazonium salt, using hypophosphorus acid. So that's the synthetic utility of that. All right, so to summarize, what have we covered? We've covered the Sandmeyer reactions, which are with copper salts. Then we covered the Shemin reaction, which uses fluoroboric acid, HBF4, to install a fluorine. Then taking the aerodiazonium and just putting it in water. That makes a phenol. And then the last one was using hypophosphorus acid to install a proton. And really, it only gives us one reason to do that, but I suppose there are others, okay? So now that brings us to the very last reaction in the whole chapter, okay? I don't think there's another one after this. Nope, I think this is the last one. And this is what we call azo coupling, okay? So it's a logical conclusion to you know, section 22.11 because you already know what an aryl diazonium ion is, okay? So it shows you another use of an aryl diazonium. So here's your aryl diazonium right here, okay? You know how to make that. You would make that from aniline, okay? And then you would treat it with sodium nitrite and HCl, and that would give you the diazonium ion. Okay, so what else can you do with it? Well, if you put your aryl diazonium ion in the presence of another aromatic ring that has an activating group on it, so I'll put here activating group, and obviously a hydroxyl is a strong activating group, so you could put strong activator. What happens is the aromatic ring with the strong activator is going to act as a nucleophile, and the diazonium ion is going to act as an electrophile. And then you can just see that it's like an electrophilic aromatic substitution reaction, isn't it? Right? So at the para position, which is this carbon here, first we make our sigma complex, which is shown down here. We show all the different resonance contributors. And then we do a proton transfer at the end, and we restore the aromatic ring. And now you end up with this what we call an azo compound. Okay, so this is called an azo compound. Now I don't know the exact name of this compound, but it says here azo coupling is used to make azo dyes. Okay, and azo dyes are the types of dyes that are used to make those bright colors in things like Fruity Pebbles. I have some Fruity Pebbles upstairs. My kids love them. Anyhow, so that's how they make those, and things like M&Ms or whatever, where they get the bright colors is from azo dyes, okay? Because they have really bright colors. And so how do you change the color? Well, you just vary the substitution on the ring. You put different substituents on, and then you end up with different colors. And I don't ask you to know anything about the colors or anything like that, but you should have an idea that azo compounds do make really good dyes. And I'll tell you what we'll do. Since that's fresh in our brain, we're going to skip this question right now, and we're going to go all the way to the question about azo coupling and see if we can find a way to make this compound. And that way I can kind of show you what the expectations are for azo coupling. So my question is to you, if you look at the ring on the left, you've got two sulfonic acids. There's one here and there's one here. And if you look at the ring on the right, it's got an amino group on it. Could anybody tell me which one of those groups is activating? Would it be the one in the blue circle or the one in the red? We're talking about activating groups. Which one would be an activating group? This goes, yeah, exactly. Thanks, you guys. It's the one in the blue circle, right? We know that this is a strong activator. Okay, therefore, this is going to be the nucleophile. Okay, and that means since the other side, sulfonic acids, those are electron, this is an electron withdrawing group, therefore it is a deactivator, and therefore this is going to be the electrophile or the diazonium ion, electrophile, okay, or the diazonium ion. So that means that our starting material, our is going to come from here, okay, that's where our nucleophile is going to come from. And our electrophile is going to come from all of this, and that's going to possess the diazonium ion. So how do they expect you to write this out? So this is what they expect, okay? Is they expect you to start with the amino compound, okay? So you would start out with your deactivated ring, okay? And instead of drawing you might be tempted, I'll just draw the diazonium salt like this. It's not the expectations of the textbook. Okay, I've looked this up in the solutions manual before. They expect you to start with the aniline derivative. So put in your sulfonic acids. Again, these are the deactivating groups. Okay, and what they expect you to write is treat it with sodium nitrite and HCl. And of course, that is going to make the diazonium ion. And then all you have to do, and maybe I should have put this all in red because this is the red part of the compound. So then what they expect you to do is they expect you to treat it with the nucleophile. So I'll change this to black. So they expect you to treat it with the nucleophile, come on, which is this compound, which is just aniline in this case, isn't it? And that's it, okay? That forms the sigma complex, and then you end up with a product. And that's it. Those are the expectations for azo coupling, okay? It is something that shows up on standardized exams, azo coupling. So make sure you are aware of azo coupling. Of course, it's going to show up on quiz 22, but I'm just saying for my students who have a few, if you're still thinking about organic chemistry, maybe even a year from now or something, azo coupling is important. Okay, so that brings us to some questions.
Mr. Dion, I have a question about the last one.
Yep.
I was wondering for like the SOH3, would that be like the 1-3 or like the 2-4 position instead? Or would it be like the one?
Oh, yeah, sorry. Yeah, I put it in the wrong spot. Yeah.
Okay.
You're right. There's an error in my structure. It doesn't change the answer. Well, I guess it would give me the wrong product. But yes, there. Thanks a lot. Perfect. All right, good. So I'm going to come back to this question in just a second, which just involves some synthesis. So these questions really borrow heavily from chapter 18 and chapter 22. So you have to be really rock solid on your electrophilic aromatic substitution. But before I get into that, I just want to show you that in terms of heterocycles, it says that we skip it, and we do. But I would recommend for my students who are healthcare minded, I'm going to leave that as an FYI. And why do I say you should read it? Because if you want to understand drugs, here you have Nexium, which is a proton pump inhibitor, or Viagra, right, which we talked about salts earlier on. Viagra is administered as a salt. It might be wise to read that section. It's not very long. And then for the spectroscopy of amines, I don't think I have any spectroscopy questions on quiz 22, but you should be aware of the IR of a primary versus a secondary amine, right? That a primary amine gives you 2 weak signals, okay? Whereas a secondary amine only gives you 1, okay? So those are probably things that you're reviewing in the lab if you're taking it with Mr. Geiger this summer. And tertiary amines, of course, they don't have nitrogen-hydrogen bonds, so they don't give any NH stretching signals. What else? The protons of an amine in the proton NMR, they show up anywhere between, it says here 0.5 and 5 parts per million. I'd say anywhere between, yeah, I guess those are good. But the chemical shift of a nitrogen-hydrogen proton can be affected a lot by things like temperature and concentration. And they're also exchanged at a fast rate, and so they don't cause any splitting, and they give broad signals. So again, I would try to remember that NH protons give broad signals, and they don't do any splitting. So they don't fit into the N+1 rule. And yeah, if you put it in a deuterated solvent, you can do a D2O exchange or something, and the NH proton will disappear. What else? Spectroscopy of amines. So protons and adjacent carbons, protons adjacent to the nitrogen atoms that show up around 2 to 3. I don't know if my students ever remember this or not, but anyhow. And then carbon atoms with a nitrogen bound to it are usually between 30 and 50. Let's see. Oh yeah, you should also know about alpha fragmentation or alpha cleavage in mass spec, and that would have been covered in detail in organic chemistry 1. And yeah, so you would have gone over alpha cleavage, and there you have it. So, sometimes students will ask me, do you have a review of all the reactions? Well, here's the review of everything that we covered. So first we started out with alkyl halides and then converting them into nitriles and then reducing those nitriles. After that, we looked at the synthesis of an amine from a carboxylic acid. So you take a carboxylic acid, make an acid chloride, then a primary amide, and then reduce that with LAH. Then we talked about aniline. So aniline shows up quite a bit in this chapter. Why? Because it's a primary amine. It's aryl, but it's still a primary amine. So you guys know about nitration from chapter 18. We can reduce the nitro with hydrogenation or a whole holy host of different metals that we can use for reduction. Then today we got into the azide synthesis, and I said that alkyl, it was alkyl diazoniums I was talking about that were explosive. But anyhow, some azides can be explosive too. But anyhow, an azide can be reduced either by hydrogenation or using lithium aluminum hydride. We talked about Gabriel synthesis, which is where you use phthalimide, then you make potassium phthalimide, then you treat it with a methyl primary or secondary alkyl halide, and then hydrazine in the last step because it's just one step, as opposed to acid, which is 2 steps. Then we looked at reductive amination, which just involves an amine, a catalytic amount of acid, and sodium cyanoborohydride. Excuse me. And what's cool about these reactions is that you form the imine in situ, right? You form I don't have to draw them all for you guys don't need me to do that. But anyhow, you form the imine in situ, and then the imine gets reduced by the sodium cyanoborohydride down to the amine. So we went over that. Then we talked about acylation, which is an acyl group is basically a protecting group for a nitrogen. And we talked about why you would do that, because then you could do Friedel-Crafts reactions, or you could do halogenation. I'll put here monohalogenation. Then we went over Hoffman elimination, and I explained the reason why Hoffman elimination works is because it avoids gauche interaction. Come on, Mr. Dion. Interaction, good enough. Then we took a look at reactions with nitrous acid, which is generated in situ with sodium nitrite and HCl, but then it forms the nitrosonium ion. If you use a secondary amine, you get an N-nitrosamine, which is carcinogenic. If you use an aniline derivative, then you can get an aryl diazonium salt. And we said with those, you can do the Sandmeyer reactions, or you can do the Schiemann reaction to put a fluorine in. You can also do cook it up with water, and you end up with a phenol derivative, or you can treat it with hypophosphorus acid to install a proton. And then we said, so we covered those already. And then the last reaction we looked at was the azo coupling. And we said that the azo compounds have very bright colors. Okay, so very interesting colors with the azo compounds. So what we'll do now is we'll take a short break, and then we're going to come back and let's see if I can find. Ooh, so close. What we're going to do is we're going to see if we can do these syntheses here. So you see we're taking this nitro compound, nitrobenzene, and then we want to make this meta-dibromobenzene. Here we're taking benzene and we're making a phenol derivative. And in the last one, we're making this para-tert-butyl benzoic acid, all from benzene. Now, I'm not saying there's only one way to do this. I haven't really looked at what I've got for some solutions. But these are syntheses that might take more than, 2 steps. Okay, these will take a couple of steps and a little bit of thinking to solve these.